All right, so we'll hand it over to Bjorn Hartman.
All right, on to the Lasting Impact Award. The WIST Lasting Impact Award was established in 2003 to recognize WIST papers that have had a long-lasting influence on our field. Eligible papers for the award must have been published at least 10 years prior to today's date. This year, the Lasting Impact Committee was chaired by Patrick Bowdish and also included Mary Ringel Morris, Takeo Igarashi, and myself. Now, for the second year, we solicited nominations for this award from the community and considered those nominations alongside strong candidates collected over the years from past committees, as well as newly eligible papers. On behalf of the committee, I'm happy to announce that the WIST 2024 Lasting Impact Award goes to Gestures Without Libraries, Toolkits, or Training. A dollar recognizer for user interface prototypes by Jake Wobbrock, Andy Wilson, and Yang Li from WIST 2007. Don't come up yet. First, got to embarrass you with some nice words about the paper. So this paper introduced a novel approach to stroke gesture recognition. The main contribution of the paper was that it took something that was generally considered to be hard at the time and made it easy and accessible. Up to that point in HCI history, it was generally assumed that writing a gesture recognizer was very hard and could only be accomplished by a small group of experts. The paper then refuted that assumption by showing that gesture generation recognition for the types of gestures that we care about in interactive systems for stroke inputs can in fact be accomplished with just a few lines of code. Namely, the algorithm in a nutshell is this. 1, you read an input stroke. 2, you place a fixed number of equidistant control points along the stroke. 3, you rotate and scale the stroke to a reference square. 4, you compute the path distance between the stroke and each of your training samples while fine-tuning the angle. And finally, you return the category of the training sample with the shortest distance. Done. The HCI audience found this straightforward to understand, to re-implement, and to use. And as a result, the approach has been re-implemented and used by a wide range of users in research, in teaching, in industry, and the broader community. That has given the work its impact. When building interactive systems, complexity often comes for free, but you really have to work hard to achieve simplicity. The dollar recognizer is a shining example that when an elegant idea is distilled to its essential core and communicated lucidly and clearly, tremendous impact can follow. In research, the paper gave rise to a host of follow-on projects that extended the capabilities, leading to a whole dollar family of technologies. In teaching, the dollar recognizer found use as both a component in student projects as well as subject of assignments in HCI courses. And in industry, the recognizer has been used in games, in interactive installations, and inspired gesture recognition in the Android framework. This paper also received several nominations by researchers in the WIST community over the years. I just want to highlight two quotes from those nominators. First said, the dollar gesture recognizer is undeniably one of the most, if not the most widely diffused WIST contribution of all time. And it epitomizes a philosophy of simplicity and replicability in technical solutions, an important characteristic that influenced others as well. So please join me in congratulating the authors on the WIST 2024 Lasting Impact Award. Please now come on up on the stage. right, I'll now turn the mic over to Jake Wobbrock to deliver the Lasting Impact Award talk.
Thank you very much. Those were really kind words. I'm very flattered. And I want to note that was Andy Wilson's third trip to the stage this evening. Andy, you could have just pitched a tent up here. Just moved in. All right, let's see. Can you help me see them? That's not my slide. Okay, so I've been to UIST many times, and I know at this point in the conference everyone's tired and wants to go eat pizza and go home. So I will try not to keep you too long. It's a real privilege for me to be able to deliver a few remarks that I hope will be thoughtful for our community, a little bit of a retrospective, a little bit of a looking back. I don't know how much sense I'm going to make entirely because I did actually have to fly in on a red eye, and I slept 0 last night. You know, when I was a grad student, I did pull a few all-nighters for UIST. I didn't expect as a 48-year-old full professor I'd be pulling an all-nighter for UIST, but here I am, having done that on an airplane. Oops, what just happened? Sneak previews, okay. This is not my laptop. So I wanted to call this talk Making Possible Things Easy, and that term comes from a phrase that Scott Hudson, that is Scott Hudson, a few years ago. Scott Hudson, so this is really special for me as well because I got my PhD at Carnegie Mellon, and Scott was a big part of my time there. Brad Myers was my advisor, and I learned a lot from both of them. But Scott Hudson said to me at one point something that stuck with me. He said, "UIST is about making impossible things possible, but it's also about making possible things easy, and both of those should be in service of people." And I think especially for the younger up-and-coming students and people kind of new to UIST, the top line we see very clearly, right? We see these amazing demos that make something that very much seemed impossible suddenly come to life, right? It's suddenly possible. And it's like almost, you know, it's just a hair's width shy of magic. And so I think we're really familiar with the top one, but UIST actually has a long history of the second one too, about making possible things easy or easier. Things that you could do already, but they're just too hard, right? They're just not accessible enough. And so we'll talk about that. But if you look at the last 6 Lasting Impact Award winners, you know, there's a mixture here as well. The top line are a lot of making impossible things possible. And aspects of that are in all of these, but the bottom line is actually making some things that were possible but just really hard much easier. For example, Morris and Horvitz's search together. You could do a kind of collaborative search, but it was cumbersome and difficult and definitely not streamlined. That's just one example. And so UIST has a long history of both of these things, and we are firmly in the camp of making something that was possible much, much easier. So our question was, how can we make 2D gesture recognition easy? This was back in 2007. There might be some people in the room who are, well, probably born, but not very old. It probably seems like a really long time ago. It's making me feel old. And so, you know, it was the year the iPhone 1 came out in 2007, to give you a calibration point. Stroke gestures were around, but not that common. Touch screens were not everywhere yet. They were in research, but not in products and stuff. So that's just kind of the context at the time. In 2003, actually, I was Andy Wilson's intern at Microsoft Research, and I got to be the first intern to ever work on the Play Table, which became what Microsoft released as the Microsoft Surface, which was not what later became the Microsoft Surface, which was more of like a laptop form factor. They originally released this thing as the Microsoft Surface. It's a vision-based system looking up from the bottom. And Andy Wilson was one of the masterminds behind the original version of this. And my job as an intern in 2003, I was only my second year as a PhD student, was let's add some gesture recognition to this so we can do things like make strokes and swipes and circle things and draw symbols and question marks and draw a box around something, those kinds of things. Things that now we frankly take pretty well for granted, I think. And so as I began to look into this, which I'd not implemented before, the main thing that stood out in HCI was actually from SIGGRAPH, and it was the Dean-Rubin recognizer, which many of you will have heard of. And it's a statistical classifier. And it's a feature-based classifier. There were 14 features that Rubin defined. You can see them listed here. And you had to know things like Mahalanobis distances and matrix inversions and discriminants and other things that I kind of knew, but not really. And as I was getting into it, it just seemed like it really shouldn't be quite this hard. And the paper didn't really tell me enough to actually build it. And so I had to work harder at this than I thought I should have to. And so I wanted something that seemed a little more straightforward. There's also dynamic programming approaches that have been around a long time, especially with handwriting recognition. You'll see me mention Tappert here in a few moments again, but Tappert had a paper on an elastic matching technique. That also seemed complicated. Gosh, I keep jumping ahead here. I have to not touch the touchpad. Okay. So what we ended up doing, I wanted to work on the interaction design. And so Andy said, just do linear time warping, which is the thing on the left. Just stretch them out in time, make the template and the candidate gesture align in time, it'll be good enough. So we did that. It didn't work all that well. And so we could kind of work with the interaction design, but not well enough. So this bothered me for a while, and after the internship, I only got satisfactory on my MSR internship. I didn't get like extra good or excellent or anything. Andy gave me a satisfactory, and I thought that wasn't very satisfactory, so that bothered me. And so it was about 2 years or 3 years later, I was talking to Per-Ola Christensen and Shuman Zai, who had released their second Shark paper, which was at WIST 2004, which won the Lasting Impact Award at WIST 2014. And they had used something they called proportional shape matching, which was an extension or a build on Tappert's elastic matching, but with zero look ahead. Essentially less elastic than Tappert's approach. It was a simpler version of that. And I thought, well, this sounds like part of what we need. They're working in a constrained space on a keyboard, so they have a certain kind of rotational frame that they're in. But that part of the proportional shape matching sounds like something we could build on. And so Per-Ola and I got to talking, and he talked to me about, don't space things out in time, space them out in space, which was ending up to be the first step in the $1 recognizer. Then we had to define a notion of orientation, which we took to be the centroid of the gesture to its first point, which is only a rough approximation of a good alignment, but it was a beginning. And then some basic stuff like scale and translation invariance, and then compare to templates. So this is just a nearest neighbor template matcher, right? There's no statistical feature extraction, anything fancy, which is part of the point. So the rotation invariance step was the one that just took a little more doing. And the upshot here was that if gestures are actually the same, not identical, but of the same class, there's not local minima in the optimal alignment for the search space over the rotation search space. But if they are mismatching gestures, there's usually local minima. That's actually a good thing, because then we don't care if it gets stuck in a local minima, because the score will be higher for gestures that shouldn't match. And then we ended up with the question of how do we find the best alignment, and we used something called golden section search, which is based on the golden ratio, and it was a much faster approach than hill climbing or just brute force. So we went with that, and it worked really well, actually. And then I'll just point out that Yang Li, who was on this paper, of course, and was just on stage, a year later published an improvement on this, which found a closed form version without the iterative approach to find the best angle. And he called that protractor, which became a cousin in the dollar family eventually. And we ended up showing that we were 7.3 times more accurate than the Rubine recognizer, and we ran 80 times faster than dynamic programming, dynamic time warping. So we had nice results there. And a big step we took, which actually at the time was, I think, not done, I think it was unprecedented as far as I know, was we actually put the entirety of the algorithm in the paper. This was back when you only had 10 pages, including references. You could not go one character over or you were desk rejected. So this was a big choice to make if we take up that much real estate on our last page. And this is pretty low-level pseudocode, actually. It's merely code, just in more symbols. And so people could write this recognizer straight off the back of the paper, and that's in fact what happened. Felt like a risk at the time. Now it turns out to have been a good choice. And we put up an interactive, JavaScript version and stuff. And then people began building it and sending me versions in Python and C# and other languages that we hadn't built it in. And suddenly, over the next couple years, we had the beginnings of what became a dollar family. So we approached multi-strokes with $, and we added protractor through Yang Li's work, and then $, protractor, and it's like they were mating and having offspring. Radu Daniel Vatvu, if you know him, he was working on point cloud matching with $, but also adopting this very simplistic, simplified approach. And then other people started implementing this stuff, and the naming scheme got a little out of hand. So there's $3, Protractor 3D, Quick Bucks, 1 cent, €1, that's a filter, 1 franc penny pincher, 3 cents, and then a few things that got a little bit like microvolt was the last one, which, but they all adopted this similar approach and they all put the code in the paper, or nearly all of them did. So there really is a whole family of these, and they all kind of built on each other and improved things that the others before them lacked. This is something I think is actually, unfortunately, somewhat rare at WIST, is that we don't directly build on each other's work that often, and for good reason. If we're doing something really novel, sometimes there's not a direct thing to build right on. But this was a case where things were, from Tappert to Shark to the dollar recognizer to the other dollars, it was all kind of building on prior work, and that just feels sort of like how science is supposed to progress. Now, I know this is kind of more invention than science, but I think it's a bit of both, and they're working together here. The thing that makes me most excited, actually, is not actually what we did per se, but what other people did with what we did, because that's, after all, the goal. Within 1 year, there was a game studio. I'd never talked to them. They didn't reach out to me. That was part of the point, right? They can just do this on their own. POW Studios built Mr. Spiff's Revenge, which won $10,000 in the Dr. Dobbs Game Challenge for Best Windows Game in 2008. I didn't even know that was a thing, but it's worth 10 grand apparently. The judges were quoted in the review of the game saying, we particularly like the gestures that were used to control the game. So here's a little clip. I'm scared of this laptop, it's not mine. How do I play? Oh, just go next. You can see that's a heart, circles, and shield. Simple stuff, but it's an integral part of the gameplay. Fireballs, and then there's a really cool one where like pow, big things come in, kill everybody. So that's exciting, and they never contacted us. We don't have any contact with them, but we just kind of ran across it, and that was exciting to see. That was within 1 year of publishing the paper, so putting that code in the back of the paper I think really helped. This is a project called Eden. By Ken, Miller, Bollensdorf, DeRose, Hartman, and Agrawala. Some of them are in the audience right now. Just a simple
Drawing
quick clip
an
where
L
you can
in
see
the
they're
stroke
using the
pad
dollar
executes a
recognizer.
command to
In
open
this
a
case,
load model
recognizing
panel.
the gesture L shape.
From
to
this
bring up a
panel, he
list
selects the
that they
models he
interact
plans
with.
to use.
Here's a paper called Air plus Touch by Chen, Schwartz, Harrison, Mainkoff, and Hudson. Also some people in the audience right now. And you can see there's gestures they make in midair that are then recognized.
This system allows us to augment touch by looking at the finger's movement directly before, between, and after touches.
So those are all dollar recognized gestures there.
This.
Let's see. Here is project on expanding the expressivity of smartwatches by Zhao Laput and Harrison. The usual suspects are still here. Let's see if I can get it to play.
Gesturally. For example, moving the watch in a circular motion, or writing a character, such as a V. This could be used for quick actions, such as activating silent mode or taking a photo.
I love that their clip
Finally,
doesn't
we ported
show
a
any
first-person shooter game to use
misrecognitions. It's lovely.
gesturally.
It's wonderful. Here's a paper by Zhang and Vogel. This actually was interesting because they used the dollar recognizer to do pose recognition, not path recognition. But they were able
We
to
developed a
adapt it for that
computer vision
purpose.
algorithm to identify
It's called
fingers and
finger-aware
hands when
shortcuts.
pressing keyboard keys. The hands are captured by a built-in laptop camera and a reflector. The system tracks the location of the keyboard to rectify it. Hands and fingers are tracked using contour analysis, heuristic rules, and the $1 recognizer.
It was a little
We
quiet,
use the
but it
system.
did say the
We
$1
developed a
recognizer
computer.
there. I promise, it's in there. This is not an academic project, but it's called InkBase. It's part of a kind of interactive sketching application. This is just an animated GIF they have on their website, but it's showing the dollar recognizer at work recognizing a triangle. And then probably my favorite example is from a fairly well-known digital artist named Zach Lieberman and his collaborator, I'm not sure his first name, Nick, maybe Felsen. And it's called Landlines. I really encourage you to try it out. On a laptop, it's even better than this video, which is just on a mobile device. I'll first show it, and then we'll describe what's happening. They're basically traveling the world. They're exploring the world by making a gesture that then matches some kind of geographic feature somewhere in the world. They partnered with Google Maps to do this. And the one on Chrome on a laptop or desktop is really lovely because it's very high res and you can make strokes. So if you go to lines.chromeexperiments.com, you can try it for yourself. But that's also using the dollar recognizer. So people found it and found it useful and made much cooler things than the dollar recognizer, after all, which is really exciting for us. So just a few takeaways and I guess points of reflection. So definitely WIST is the place for novel, inventions, right? The first time something's been done. That should be here. We should never give up our coin of the realm. That's super awesome. But also it is a place that has a long history of contributions that make known things much easier to do. An example from the early days of WIST is all the work on UI toolkits, right? And ways to make interfaces just much, much easier and more efficient to build. Scott Hudson, Brad Myers, others have done lots of work in that space early on. For maximum impact, I think we do need to continue to prioritize both of these things, not just one or the other. And this means, I think, for example, trying to make your contributions easy to take up and use by others. I know that's hard to do with certain things. They don't all amount to a pseudocode algorithm on the last page of your paper. But you can still kind of keep this in mind and see to what extent that's possible. Enable others to replicate and maybe test your inventions, especially if they want to compare against them. Also takes a bit more effort, but if you think about it from the beginning of the project, I do think it's easier than trying to add it on at the end, which is tougher. Andy was talking about how, a lot of contributions are kind of black boxes to the outside, but what we tried to do was really an example of a white box, right? Really shining the light on the internals and how things work, making it really easy to do. One of the nice compliments that we've gotten is how many people are teaching this in their classes. Rob Jacob actually just told me that today, that he's still teaching it because intro-level students can actually understand what's going on, and it gives them access to gesture recognition in a way that doesn't intimidate them because they have to invert a matrix or something. And then, think beyond your WIST publication. Like what's your invention life beyond the publication look like? I do realize some of these things are at odds with commercial incentives, so, we do our best. And that's it. Thank you. Appreciate your time. I guess I was told that we can maybe have a little Q&A. I don't know how much time we have, but and I would really implore my co-authors to come up here for these. You're not getting off the hook. Come on. Andy Wilson, 4th time to the stage, please. Come on, Young. We'll field these together. The hard ones you guys get.
Okay, so this might be easy, but still, we can get started with that. So a lot of times when you submit a paper which is easy, a lot of times you might get reviews which are, say that, well, it is easy, so do something else. So did you get this paper rejected ever? Tell us the rejection stories.
That's a good question. I will tell you that it was accepted the first submission, but it was the lowest rated paper that got in. And I only know that. That's not no one violated a confidence. I only know that because I was on the program committee. And so I was out of the room, of course, but when I came back in the room and I saw it actually got accepted, it was way down the list. There were like 5 or 6 papers above it that got rejected, and somehow someone thought that might be worth accepting. So very nearly. Yeah, and you're right. You get that, right? It's not hard enough. It's not fancy enough. I think that's a point of reflection for us, right? There's like Bjorn said at the opening remarks. There's good ways to be simple, and there's hard ways to be simple, right? Being simple shouldn't be taken for granted as a trivial thing to do, right? Simple's good and not always easy to achieve. Yeah.
Hello, Alex Solwell of Google. Also confessed to one of the implementations, maybe linked.
That's right. You sent me one. Yeah.
Yeah, I really loved like the whole project. I was wondering if you can comment. Do you see any like nuggets in sort of the current state of AI hype, where you're desperately waiting for some cool tool to accelerate things?
Yeah, he's with DeepMind.
Well, I think in terms of a task, right? So we have a much better technology to actually do this now. But I think what people should take away from this work is that, as Shakes actually said, right? It's a white box approach, and people really know what's going on under the hood, right? So it's not like something like these large models. We don't really know actually what happens. So another thing is about the benchmark. I think that's what's really valuable for our field, to directly build on top of each other's work, right? So you can really check the progress. I would just talk about this.
Good answer.
Thank you.
Hi, thank you for the great talk. I'm Vivian from CMU. You know, as much as we include our code or open source or repositories in our current work, I feel like sometimes with the amount of research that's coming out, it can be a little difficult to publicize that work and like hope that people read and like use your work. I'm curious for this paper if there's any ways outside of just including the code that you were able to publicize and do outreach for your work, and if you have any tips for like in the current climate of research.
I mean, it's the webpage. Jake had the foresight to put together a nice website where he collected all the implementations as people sent them to him. And you know, I think one of the things that was important was we decided to not patent or do any protection. We made it in the public domain straight off, and that was something that we thought about a little bit, and I think that was key. If you think back to that time frame, there was all sorts of thinking about codecs and how they were being protected by the companies, and people were not using some of those things, and I got to witness some of that at the company at Microsoft. And so we decided, you know what, and I did this probably without permission, to just not worry about it. And I think that was an important fact, right? Important decision. But really, I'll say, really, the website was the key. Those two things together.
All I was going to say is, in that very wise choice, you made up for my satisfactory rating.
I didn't realize you're harboring like this angst. Good job, Jake. You've done good.
Thank you.
Hi, Bingjian Huang from the University of Toronto. Thank you for the great talk. I think my question is surrounding, as we're having more and more hardware research in the WIST community, apparently open sourcing hardware is pretty hard. And also for people who want to use the open source hardware is also hard because they need all the, the machines to manufacturing the hardware. I wonder if you have any thoughts or any future vision on this side. Thank you.
Thoughts about hardware? And open sourcing hardware?
I mean, I can say one thing short. I'll just say one thing really short, but then you still have to do it. Which is, I don't know how many projects bother to make a project dedicated website, bother to publish their circuit boards or their specs that could at least sometimes could be reprinted by somebody. Maybe, I think we try not to put stuff in WIST papers that take up space that feel, like Mayank said, kind of the easy parts or the familiar parts. We try to make it all kind of novel and shiny. And we've created incentives for each other to do that. But the extent to which we can get the banal stuff that makes it possible out there, like Ruben could have written his paper in a way that was a lot easier to actually build his thing. And a lot smarter people than I have built it, but well, actually Young built it for us, so that's proof of what I just said. But a lot of us don't, there's a similar movement to try to do plain language summaries of research that are shortened versions that are digestible by the general public, especially in the accessibility community. We're trying to do more of that. That's another example of trying to make our stuff, I don't want to break it to everybody, but no one reads our papers except each other for the most part, right? For the most part. I mean, there are some exceptions, but for the most part, no one's out reading WIST papers. No product groups read WIST papers. It's very rare. So we have to, I think we're good at making videos that help get those things out, but there's more that we can do there. But it takes effort, and then often we get the paper, we check the box, and we move on. And I think we just want to question that a little bit.
This really doesn't have anything to do with hardware, but I do think it's really interesting to watch how the AI community has sort of progressed into this mode of having a project page that's maybe hosted on GitHub.io, right? And then you have the link to the paper, to the source code, to the demo. And it's hard to imagine, but back when we were doing this work, people weren't really doing that. Is there an analog to that for hardware? I don't know. Maybe somebody can answer that question. I feel like people have tried, but it hasn't maybe stuck.
That's already a pretty good answer, yeah, thanks.
Thank you.